Welcome to the continuing lecture on non-conventional machining processes. So, the next process is going to be ultrasonic machining process. The basics of ultrasonic machining process involves a tool made out of ductile and tough material vibrating at a very low amplitude, very high frequency and a continuous flow of abrasive slurry is there. In a small gap between the tool and the workpiece, there is a machining. So, if you look at it, this is the vibration which is given, which is attached to a tool here. So, this is called as a sonicator. So, that sonicator, this you create piezoelectric sonicators are available. You create the vibration and this vibration whatever you create is getting amplified by this portion called horn. So, this horn multiplies the amplitude. Vibration will be 21 kilohertz, there is no change, but as an it will be a very small amplitude. Piezo crystals, when you stack together, they give only 1 micron, 2 micron displacement. So, now you have to increase the displacement to 5 micron, 8 micron, 10 micron, 15 micron. So, what we do is we attach the transducer to a horn. The function of this horn is to multiply and it has to enhance the amplitude. Then this amplitude is connected to a tool. So, this is how the tool looks like. This is the tool. This is a tool, right. The tool vibrates and then when it vibrates, it moves up and down. So, here you have the abrasives which flow in the media kept there. So, the abrasive when it moves here along with the water media, it forms a slurry. So, the slurry is filled on top or the slurry can be pushed from one side and sucked on the other side. You can fill it up and then it can do. Now, what happens when the vibration is given, right? When the vibration is given, so the tool comes in contact with the abrasive. Assume that you have a bat, tennis bat, table tennis bat, ping pong bat. You have a ball, the ball bounces. So, now when the ball is bouncing, you are trying and you have a hard surface, the table. So, now you try to move down the ping pong bat. So, the ball will try to hit. When you go down and down and down, the impact can be large. The ping pong ball will go vibrating faster and faster and faster. After some point of time, the amplitude dies. That is a long term story. But when if you move from here to here to here, you can see the frequency increases, the impact increases and then it can try to make some indent on the table. So, in the same way here, it is not one ping pong ball, there are several ping pong balls, these are abrasives. These abrasives are loose and they can move easily in the media and now you start vibrating. When you start vibrating, the abrasive hits the tool and then it tries to come and hit at the workpiece. So, here there are 3 steps which are involved. So, here the abrasive is here, this is the workpiece, this is the tool. As and when the abrasive moves down, the tool moves down. So, the tool comes here, this is step 1, this is step 2, where the tool is at a very large distance away from the workpiece. Next, the tool moves down. So, it is step 2. Now, in the step 3 what happens? The tool comes here, the abrasive comes here, this is third step. So, when this happens, it is almost similar to abrasive jet machining. There is a chipping off happening from the workpiece, which can be used for removing and taking away material. So, here what happens? The chip gets moved away along with the abrasive and slurry. It moves away. So, and whenever it is vibrating at 21 kilohertz, it tries to create a cavitation effect. This cavitation effect also tries to remove the loose particles which are sticking on to the workpiece and then whatever is the feature to be generated, it gets generated very nicely. So, ultrasonic is very effective when we use brittle material machining. It can do very high aspect ratio machining. That means to say very small diameter small, very large length can be done. This high aspect ratio holes are done using this ultrasonic machining. So, the tool is gradually fed with a uniform force. The impact of the hard abrasive grain fractures the hard and brittle workpiece surface, resulting in removal of material in the form of small wear particles. The tool material is always tough. Why? Because if the tool material is also hard, then there will be chipping off of the tool material as well as the workpiece material. Here I do not want the chipping of the tool, so I try to use a tough material. So, this tough material will give some leeway of indentation inside the tool, but it will not have a tool wear. So, that is why we always choose the tool whatever is there as a tough material, and this tool is braced. You remember we studied bracing in welding, is braced to the horn, and this horn can be screwed or it can be again joined to the piezo actuators, right. So, the slurry can be recirculated, put a filter and then it can be recirculated. So, the mechanisms can be hammering of the abrasive particle on top of the workpiece, impact of free. So, this is whatever I said, tool moving down. So, the other way around is there are free abrasives which keep coming, hitting the surface and going. So, the load need not be happening here, because there are random in nature. When the tool moves up, still the abrasive slurry can be flowing down. So, the impact of free abrasives on the workpiece can lead to a removal of material. Cavitation, as I told you, when the ultrasonic creates up and down motion, it can create bubbles. These bubbles have very high local pressure. When it explodes, it tries to remove material. There can be a small chemical action with the fluid, which is almost negligible. So, these three are very important material removal mechanisms as far as ultrasonic machining is concerned. M.C. Shah made a model. So, I am just presenting you this model to understand what will be the material removal rate and who are all the key players in the material removal rate as far as ultrasonic machining is concerned. So, there are assumptions made while making the model by M.C. Shah. The rate of material removal is proportion to the volume of the material per impact. Okay. So, what he says is, he says the rate of material removal is MRR is proportional to the volume of material per impact. So, you know one abrasive impact. So, when I know in one slurry how many abrasives are there, I multiply it and then I say the rate of workpiece material removal is proportion to the number of particles making impact in a cycle. So, this is what I said here. The rate of material removal is proportion to the frequency, how many times I hit. All impacts are identical, all abrasives are identical. So, because the abrasives are random in nature, I cannot do it. So, what I do is I make every abrasive spherical, and all the impact what happens on one abrasive also tries to happen on the other abrasive, the same impact. So, by making all these assumptions, I am able to calculate the volume of material removal rate Q. Q is nothing but is directly proportional to volume of material removal per impact, right, V, and Z is the number of particles present there, and nu is the frequency. By multiplying this, right. So, I know per impact what is the amount of volume removed. Then I know how many abrasives are there in one impact, abrasives in one impact. So, what does it mean is you have an abrasive, we are now currently taking one, there can be 5. So, number of abrasives per impact per cycle, then the frequency is how many times I do. So, through multiplying all these things, I can try to find out the volume of material removal. The proportionality can be removed by a constant K. That constant K is a workpiece, tool material and the abrasive material interaction. So, as I said earlier, the mechanism of material removal, you can try to have a position A, which is the mean position, indicates the instant the tool face touches the abrasive. So, the tool moves from C position to B position, the tool moves from C to B, that is every cycle, it moves from C to B. So, when it comes to a mean position. Mean position is between C and B, halfway is O. Halfway is O. At the position A, the abrasive comes in contact with the tool. So, now you can clearly say C, O, A and B. This is the amplitude, this is the mean, and this is the point when there is a contact coming in with the workpiece, right. So, from here, from the mean position to the O position, see the total time t is nothing but C, B, B back to C is t. Now, when I move from O to B, it is t by 4, that is what is told, t by 4. Now, I do not know the exact position where A will come in contact and what is the abrasive size. We are assuming it to be same, but in reality there can be a change. So, the time taken to move from A to B is delta t. So, the period of movement from A to B represents the impact. So, the impact time is delta t. The indentation caused by the grain on the tool and the workpiece at the extreme position of the tool from the position A to B is h. So, what is h? So, the depth in which the abrasive tries to indent into the workpiece is h, and when it tries to indent, it is also possible that it will try to indent the workpiece. So, there is going to be a h which happens here, h w, then this is h t, small indentation, right. So, this is what we are trying to say. So, now we can try to go further and understand. So, d is the distance, or we can try to say the tool and the workpiece, whatever is the distance is d, right. So, now what we can do is we can start calculating the material removal rate, which is little on the higher level for this course, but I just wanted to expose all these things for you. So, the plot between MRR and the feed force, the MRR increases with the feed force. So, this is MRR and this is the feed force. So, it goes like this, as the units will be millimeter cube per second or something, feed force will be in Newton. So, as and when the force keeps on increasing, what is the force? Critical feed force is this force, when we apply a load on top of it, that is the feed force. But after a certain feed force, there will be a decrease. So, this is the maximum, and after hitting the maximum it reduces. Why does it reduce? The abrasives gets crushed. So, what are all the process parameters which are very important in ultrasonic? The frequency, which is almost constant, 21 kilohertz, the amplitude, which can vary from 1 to 10 microns, the static load, which can vary from 1 to 10 Newton, the hardness to tool ratio, this is very important, the grain size is many a times which is less than 50 microns, which is always less than 50 microns. The concentration, we will always go 0.3, 30% to 40% is the concentration limit. So, these are the process parameters and these are the values which generally we use for ultrasonic machining. So, when we try to have a relative hardness, glass, if you try to take it as 100, brass it is 6.6 is the material removal rate, tungsten it is 4.8, titanium it is 4, steel it is 3.9 and chrome steel it is 1.1. So, you see comparing to glass what will be the material removal rate. So, when we plot with respect to grain size, so this is the graph which talks about it. So, the material removal rate also increases with the mean grain diameter d, but after a certain point it will crush. So, the material removal rate is reduced. Theoretically speaking, it will try to continue a straight line, but practically it will start crushing. So, we have to choose at this point the material removal rate. The concentration of the abrasive is also the same. If you have more and more and more concentration, it is truly speaking it has to remove lot of material, but moment the concentrations are very high, then majority of the energy is spent between striking and striking of abrasives. See, when you try to take 10%, you will try to have, these are the abrasives. When you have 30%, it is something like this. When you have 80%, it will be like this. So, in 80%, what happens? Rather than the abrasive tool abrasive hitting at the workpiece, it will be more of abrasive hitting. When abrasive hitting, it does not come in contact with the workpiece, the abrasive gets damaged. So, there also you have a maximum saturation point, afterwards it is almost constant or it decreases. So, the concentration of the abrasive directly controls the number of grains producing impact. The MRR is proportion to C 1 by 4. So, after C rises to 30%, the MRR is not very fast. So, if you see the roughness which is getting generated with respect to mean size, moment the size of the abrasive goes large, the chip what is getting extracted is also large, the cavity which is formed is large. So, roughness is high. So, as and when the abrasive size goes high, the roughness is also high, right. So, then there is a difference between tungsten carbide as an abrasive and glass as an abrasive. So, if you see glass as an abrasive, glass when it tries to hit at the workpiece, it also shatters. So, because of that the glass tries to create lot of scratch. The material abrasive, the average roughness is very high when we use glass. So, depending upon the surface finish on grain size, the surface finish is more sensitive towards grain size in softer materials like glass. Harder materials like tungsten carbide, they have very less impact. The brittle fracture, the fragment size in harder materials is less effective by impact of particle size. So, this is the schematic diagram as I have already explained. This is the acoustic head. So, here it is all called a sonicator. This is the horn, this is the tool. Tool is in turn attached to a small profile whatever you want. So, there is a feeding unit, because when you are trying to drill a hole, there has to be feed which is given. It can be based on gravity, you can put a weight here, or there can be a solenoid which comes and do it. So, there is a feed unit, there is a tool which is there, abrasive slurry concentration we have already seen, body with the table is also seen. So, we can use air compressor to pressurize the feed, or we use a solenoid, or we use gravity. So, acoustic head is to produce the vibration, it has a generator, a holder to hold the head, a concentrator is to mechanically amplify this. So, we are talking about the horn. So, there are various types of concentrators, I called it as horn, you can also call it as concentrator. There are stepped concentrator, there are exponential concentrator, there are conical concentrator. Exponential concentrator is the best, but manufacturing difficulty is there, that is why we always go for a taper one. So, the horn which is used is always taper. So, the horn is used for multiplying the or amplifying the amplitude. Slurry concentration, we have seen boron carbide, silicon carbide, then you have corundum, alumina, diamond, boron silicon carbide, all these things can be used. The best one we use is always B4C, which has a very high hardness, and here since the temperatures are not very high, the boron carbide does not dissociate. So, we use boron carbide as the material here. Silicon is also used on glass. The cutting time with silicon is about 20 to 40% more than that of the B4C. Diamond dust particles also can be used. The water is used for a slurry making. Then the advantages, very high aspect ratio holes can be made, the array of holes can be made. Basically, you move the table, the ultrasonic can be done. It is very slow as compared to drilling. Fragile materials can be used for machining. So, there is no thermal damage at all. What is the limitation? It is a slow process and it is used for only small size workpieces. Large workpieces, holding, deflection, all these things come. They find a lot of application is ultrasonic machining, medical applications, and also in micro size feature. The next process of interest is going to be chemical machining process. In chemical machining process, as I told you, we will try to have a chemical as an etchant, which is always an acidic. So, this etchant is mixed, is diluted with water and it is filled inside a tank. So, that is called as the chemical reagent. So, now you try to keep the workpiece, and on top of the workpiece you apply a maskant, or that means to say you apply a mask. So, this mask tries to protect the material where all it has to be etched. In order to have continuously etching and the slurry should not get deposited in the machined area, we always use an agitator to always create a vortex. So, this vortex disturbs the slurry material and it tries to remove from the space where it is getting machined to the bottom. We can try to have a heating element. So, this heating accelerates the phenomena of etching. The chemical machining is a unique non-traditional machining process that removes material through chemical dissolution, eliminating mechanical contact and tool wear. So, here there is no cutting force. So, very fragile sheets can be made. If you see Lord Krishna ka photo, they etch it, or Jesus ka photo, they etch it, and if you want to write some Quran words, they etch it. They are all done by very thin sheet, they are all done by chemical etching. So, the method is particularly benefit for machining thin, delicate and intricate components. It ensures uniform material removal and along selective machining through mask. So, if you do not put the mask, what will happen? Uniform thinning will happen. You have an object, you put into an etchant and you start rotating the cylinder, you will have uniform etching happening all around the cylinder. And see, there are multiple things, you have to rotate it, you have to reciprocate it. So, when you reciprocate and rotate, you will have a thin. Suppose if you do not reciprocate, you only rotate, you will get a taper. So, you can play with the shapes what you want. So, if you are trying to use a solid, then you will try to remove material. If you want to do selective, you try to put a mask. You can also do very high aspect ratio hole. So, this both sides also can be done. So, you can generate a profile like this. So that you try to create a hole possible. Additionally, the absence of heat here, there is no thermal damage to the workpiece made. So, what is the process? The chemical machining process begins with a cleaning step where the workpiece is thoroughly cleaned, then a mask is applied. If you want to do selective, a mask is applied, then there is an etching stage, then finally the etching is over, the maskant is removed and the workpiece is cleaned, and we remove all the traces of the etchant which is there, so that corrosion cannot happen. So, advantages: no mechanical stress, no machining, so can machining complex and intricate shapes. So, it can do a full machining, or it can do engraving on top, or it can also do a taper possible. So, work on hard, brittle and thin material can be done. It is suitable for batch production. Chemical handling is always a challenge. The material removal rate is slow, limited to thin machining, and it is not ideal for mass production. So, aerospace components, many of the transformer components, very thin laminates are made out of chemical etching. So, electrochemical machining is the next process, which is advancement of chemical machining. I wanted to accelerate the machining process. So, here what do I do is I attach it with electricity. So, electrochemical machining process is an advanced non-contact machining process based on electrolysis, the same thing, functioning as the reverse of electroplating. There it was only etching. So, here it is electrolysis happens. In plating what happens? You have an anode, from an anode you try to remove material and deposit on a cathode. While depositing, I do not allow this to deposit, I remove the material off. So, from the anode there is material getting removed, it is not getting deposited on cathode, I move the electrolyte out. So, that is electrochemical machining. So, the material removal through ion movement in an electrolyte ensuring uniform material dissolution without mechanical stress is electrochemical machining. So, here you use a tool called a cathode, then you attach the workpiece to the anode. So, you give a tool profile whatever you want. Based upon the tool profile and the distance what you maintain, the current density is what is there, the amount of the electrolysis whatever happens, the amount of material dissolution which happens changes. So, based upon the tool profile you can create the workpiece, the profile what you want. Here there is no tool wear, there is no heat affected zone, there is no heat generated. So, it is a very wonderful process. The tool remains unaffected while the workpiece dissolves, enabling the high precision and elimination of tool wear. The process is ideal for making complex shapes, hard material and smooth surfaces. Very high aspect ratio holes can be made, very large complex curvatures if you want can be made. You can use it like sinking, you can use it also like milling. That means to say, like in milling operation, I used to have a tool, I rotate a tool and I move the workpiece in the XY plane. You can try to make a pocket. So, this process, the advantage is there is no heat and the surface finish is extremely well. So, the electrochemical machining, the dissolution rate is higher when the gap is smaller. So, basically it depends on the current density. So, it is an inverse relationship between the current density and the gap. So, this is negative, this is positive, and what we are trying to talk about this is the gap. Depending upon the current densities, the material removal rate will be as and when the tool moves down. So, if you keep it at one point and do it, the etching will happen and it will stop. So, now I have to keep moving the tool. So, there is a feed rate given. As the tool moves downward, the workpiece surface gradually takes the tool shape, achieving the uniform gap at steady states. High pressure electrolyte is used such that very small gaps can be maintained, the material removal also can happen. Very large currents will be used. Current densities will be phenomenally high. The voltages will be small, the current densities will be very high. So, you can see here the material removal rate is 1600 millimeter cube per 1000 amps. So, it can remove 16,000 millimeter cube of material, nearly 30 times faster than the conventional, but the energy consumption is very high for electrochemical machining process. So, this is how the process looks like. So, I give a constant feed from the top, this is the tool. The tool does not come in contact with the workpiece, there is no maskant used. The tool has to be a conducting material. Whatever is the profile on the tool will be replicated on the workpiece. So, the tool is given the negative potential, the workpiece is given the positive potential. The tool can rotate and move in the XY plane. And so, now what is happening in the entire thing, the tool, the workpiece, the stand, everything is sunk inside a electrolyte. This electrolyte can be acidic, can be neutral, can be basic. So, what do? I try to have NaCl plus I try to mix it up with water, maintain some mole percentage and then I try to fill up the electrolyte. I can also take HCl, I can also take HNO3, depending upon the workpiece tool combination, you can try to choose it. So, now in the presence of the electrolyte and Faraday's principle coming into existence, there will be a material removal rate which is happening. So, the feed is given from the top. So, the electrolyte whatever is there is pumped inside, this is the power supply, the electrolyte is pumped inside and then the electrolyte is also removed from here. So, we maintain a constant level and whichever gets removed here passes through multiple filters, they remove the sludge and then it is getting recirculated. The electrolyte can be pressurized or it can be free flowing. The material removal rate remains unaffected by workpiece hardness, making ECM ideal for low machining material and complex shapes. Additionally, there is no tool wear which makes this process more versatile than any other non-conventional machining process. Although ECM involves electrochemical machining, the tool and the workpiece experiences significant force due to high pressure fluid in the gap. The Faraday's law governs the process, stating that the material removal rate is proportional to the electric charge which is getting passed. Additionally, different substance dissolves or deposits in proportion to the chemical equivalency of weight. So, these are the advantages. Extremely hard materials can be moved, no tool wear, it is faster than the conventional machining process, you can get up to 25 microns accuracy. The disadvantages, it has, since it is reacting and there is a dissolution happening, the maintenance of the equipment is very hard. The electrolyte solution has to be constantly maintained. you should also understand when the current passes through a liquid, there is a hydrolysis happening. So, the water will get evaporated. Then once the water is evaporated, the concentration level goes high. In order to maintain, we always keep on adding water. Steady voltage potential is required if hydrogen, because when you apply water and when you apply an electrolyte there, it is going to make H plus and OH, right. So, this H plus is hydrogen. So, if hydrogen is liberated at the tool surface, then it is possible to suffer from hydrogen embrittlement of the surface. So, the hydrogen, because water dissociates, it produces hydrogen. This hydrogen can enter into cracks, and these cracks while putting in service condition can lead to damage. So, this is a disadvantage which happens in this process. So, here because of that, the fatigue property always is little compromised when we use electrochemical machining process. So, the same electrochemical machining process can be used for electrochemical cutting, it can be used for electrochemical broaching, drilling and deburring. So, you can see here such parts when they are machined by electrochemical machining process. Turbine blades can be made, thin slots have been made for roller bearing, and the airfoil compressor discs are also made out of this process. So, electrochemical machining process is a very versatile process. So, as I told you here, you can see here the electrochemical can be blunt with cutting, broaching, drilling and deburring. We will try to show an example of electrochemical grinding. So, every other process is grinding the same, but here what we do is we try to have abrasives which are metal bonded, so that the negative terminal can be given here and the positive terminal is given to the workpiece. The flood coolant what we use in grinding, here we will replace by an electrolyte. Rest all is the same, the workpiece is given. So, you can see here the metal bonded wheel is given the negative, right, negative potential, positive potential. There is a slurry which is there is a electrolyte which is flowing, which tries to create the electrolysis and dissolution happening. So, the advantage, the wear is reduced to a large extent, material removal rate is phenomenally high, the heat generation at the workpiece is removed drastically. Electrochemical grinding is a hybrid process wherein which it is a combination of electrochemical machining and conventional grinding. The material removes through anodic dissolution assisted by mechanical grinding. So, first dissolution happens as well as the mechanical grinding removes the material. So, ECG is mainly used for hard materials and delicate components are made out of electrochemical grinding process. The setup consists of a workpiece which must be electrically conductive, grinding wheel which is also conducting grinding wheel. So, metal bond is used, the abrasives can be diamond. So, here ECM is used by dissolution process, we try to remove material and then we try to do grinding process wherein which the mechanical action removes the little bit of abrasives, the material whatever is there. So, it is grinding is mechanical. So, we use both combination. So, that makes the process very efficient. The electrolyte system flows between the workpiece and the grinding wheel, facilitating electrochemical dissolution and deburring. A DC power supply of low voltage, very high power is used. A pump is used for maintaining and filtration of the electrolytic system. So, this is how it looks like in reality. So, this is the wheel and then you remove it. So, here is the wheel. The abrasives are not 100%. If you see here, it is bonded to a disc. So, here the abrasives are bonded in metal bonding. No heat is generated. As I told you, hard and tough materials can be done, no tool wear, free from burrs. The disadvantages are initial cost is very high, only conducting material can be done. It can be slow in terms of material removal rate as compared to that of grinding, but many a times it is also faster. So, this point has to be considered, it can also be higher at need base. Electrolytic dissolution, so we have to be careful in handling it while. Thank you very much.